All right, welcome everybody to today's Forecast Decision Training Division, or FDTD Go 16 Applications webinar. We want to build on the success of the Visit Satellite Chat and the WDTT Storm of the Month by having presenters from the field lead these brief presentations in a somewhat more formal, about a 20-minute discussion period, followed by about a 10-minute question and answer period at the end. And at the end, we'll be asking for people as well, for volunteers for future sessions. So if you see something interesting in Go 16, don't hesitate to contact us, and you can be leading one of these in the future. So without further ado, let's turn it over to Phil Schumacher, who is from the Sioux Falls WFO.
Okay, thank you, Dan. Like I said, I'm Phil Schumacher. I'm the Sioux in Sioux Falls, South Dakota, and I feel privileged to be asked to do this discussion on the split window difference, or the 12.3 minus 10.3 micron brightness temperature difference. So as Dan alluded to, this is part of the FDTD Satellite Chat Library discussion, and they have a whole library of discussions that go back into 2016. So if you missed one of these discussions, you can go to the website that's listed below, and you can download those discussions and listen to them either for yourself or for your staff at any time. And this one will be recorded and be made available shortly. So the typical rules apply for the discussion. I will try and keep it as close to 20 minutes as possible, so that it gives all of us you 10 minutes to ask any questions that I will try to answer. If I can't answer it, Scott and Dan have offered to answer the questions. They have a lot more knowledge than me on this. And then that will go till about 2:30 Central Time. After that, we'll probably close the discussion, but I will provide my email address, so if you have any questions for me, I will be more than happy to answer any emails that come in. And finally, just remember, please do not press hold. That will result in everyone getting to hear the NOAA weather radio broadcast from your CWA. So the split window difference. This is something that we're actually somewhat familiar with in some ways. We've been looking at it for the fog imagery, for instance, looking at 3.9 brightness temperature minus the 11.0 brightness temperature off of GOES 13 and GOES 15. But what's nice is with AWIPS now, it does now an on-the-fly difference between individual channels. And what we're going to look at is the brightness temperature difference between the clean, the 10.3 micron, and the dirty 12.3 micron IR channels. And what I'm going to do is use an example actually from Florida, which may seem ironic since I'm up in the central part of the country in Sioux Falls. But the reason I actually chose Florida is I've been looking at this split window difference for the last few weeks, looking for examples of convection, and specifically cooling of moisture prior to convective development, to see if there were tips in the brightness temperature difference that may help forecasters for IDSS or for forecasting purposes look for convection differences. And as I was doing this, I noticed this really cool example over Florida one day, and that's what I'll share with you today. So just as a brief review, what we're looking at is, again, the 12.3 minus the 10.3 micron windows. And they're both considered IR windows, in which case most radiation that's emitted by the Earth's surface is able to reach the satellite. But if we zoom in to the two channels, here's 10.3 is here, 12.3 to the right, you notice that with the 12.3, this is the brightness temperature with colder going up. You see that there's peaks where there's colder temperatures that would be emitted in the U.S. standard atmosphere. And that's because at around 12.9, a little over 11.9, I'm sorry, 12.1 and 12.5 to 12.7, there's areas where water vapor will absorb the IR and then re-emit it back to the atmosphere. And so if you have a lot of low-level moisture, more of that moisture will get absorbed and re-emitted back up to the satellite at a different temperature. And so that's why it's considered a dirty IR channel, because with cooler, the more moisture there is, the more that's re-emitted from a higher level in the atmosphere, compared to the 10.3, which has almost no reabsorption by water vapor or any other atmospheric constituent. And so you can then surmise that there may be more low-level moisture available, which is one constituent for convective development. And there are the peaks that I was talking about before. So examining this channel over the day can be really useful to looking at how atmospheric moisture may be changing and how the atmosphere may be becoming more prime for convective development during the early to late afternoon. So what we're going to do is we're going to look at this difference, and this is a color scheme that I came up with a lead forecaster here at the office. The brown is when the brightness temperature difference is 0. Once you get to kind of the lime green, you're getting to 2 to 3 C difference. And once you get to the blues, such as over here, you have about a 6 C difference in the brightness temperature. And then you get to much higher values, which aren't as important. So we're going to focus on the Florida Peninsula again, and specifically we're going to look at this one point here just northeast of Naples, Florida. And we're going to look at the brightness temperature difference as it evolves during the morning hours. We're going to start just before sunrise and then run through early afternoon. And all these images were taken from March 29, 2017. And to kind of set up the discussion, I'm going to look at graphics of plots of the brightness temperature difference and various things rather than looking immediately at the satellite picture. So we're looking at the brightness temperature difference here, starting at 1132 UTC and going out to 1732 UTC. And what you notice is that there's generally a pretty linear increase in the brightness temperature difference as you go from just before sunrise up to local noon, right around 1630 Z or so. And then it becomes fairly steady and a little bit more chaotic from 1632 to about 1732 Z. So, one of the things we kind of get through the training is that maybe this brightness temperature difference is telling us that there is more moisture available through the day because we're getting this larger difference. But if that's what's really happening, are we really seeing a significant increase in moisture across central Florida during the morning hours? Well, if we go ahead and we look at the reflectance, we can start looking at a little bit of what else might be happening. So the blue line here is the reflectance from the 0.64 micrometer imagery, or the red, which is kind of what we're used to looking at for visible imagery. And the reflectance scale is over on the right. And you can see near sunrise and also sunset, reflectance is going to be very low because the light is very diffuse and it's not scattered as efficiently. But as you go later into the day, the reflectance will gradually increase as the sun becomes higher in the sky and more light is reflected back. Of course, since we're in the Florida Peninsula, it's pretty green there, so a lot of the red light is being absorbed by the plant life there, and so you never get very high reflectance until we get to around 1632 Z, where you see similar to the time where we see the brightness temperature difference fluctuate, we start seeing the reflectance fluctuate, red reflectance fluctuate as well. So that's probably indication that we're getting clouds forming, or cumulus forming. So is the increasing brightness temperature difference here that we're seeing beforehand due to cloud cover or not? Or is there something else still going on? So another thing we can look at is we can actually look at the 10.3 and 12.3 brightness temperatures, which are on the bottom here. And when we look at that, we see in the morning, they start off fairly even. Not surprisingly, we were near 0. And they gradually spread through the morning. And there was a gap here where we had no data. And then you can see as we hit 1632, just as our red reflectance starts fluctuating more, you see the brightness temperature starting to fall and rise and fall. And so what is that telling you? Well, what that's telling you is that there's probably clouds beginning to form because essentially you're getting a mix of cloud and ground, and so the IR is being re-emitted from both the cloud and the ground area within the pixels from most likely the cumulus, since these values are still pretty warm. The 10.3 still just under 30 C. And so you get an averaging over the pixel, the 1 kilometer by 1 kilometer pixel, or 2 kilometer by 2 kilometer pixel, sorry, and the bare ground. And you see the temperatures fluctuate depending on the fraction of cloud cover that's in that pixel. And you get that sense also by looking at the red reflectance, although this is a higher resolution picture off the visible reflectance than you get off of the IR. But you can see that even despite the cloud cover, the difference, even though the brightness temperatures vary by quite a bit, as much as 5 to 10 degrees, the actual difference doesn't vary pretty much. So it's probably not the cloud cover that's really causing the increase in brightness temperature. So again, what are we seeing here? Why are we seeing this rapid increase during the morning hours? Well, the last thing we can look at is we can look at an actual observation. So I got the observation out of Winter Haven, Florida, which is fairly close to the point that we're looking at. And you can see initially the 2-meter temperature out of Winter Haven is much warmer, about 5 to 7 degrees C warmer than the temperature at both 10.3 and 12.3. But as the sun rises and we get later into the morning hours, you can see that it equals the brightness temperature at around 1352 C, and then actually is cooler than the 10.3 brightness temperature and equals more like the 12.3 micrometer brightness temperature by the time we get to 1552 C. And then as the clouds form, it basically will be the same or warmer than the 12.3 because you start sampling the air mass above the ground. But of more interest is the green dots, which show the dew points. And you see that actually the dew points are falling through the morning. So we're not seeing an increase in moisture, at least at the surface, during the morning hours in Florida. In fact, we're seeing a decrease in the moisture because as the boundary layer deepens. So what's happening? Well, the answer comes when you look at the Tampa, Florida sounding. When you look at the sounding from that morning, it's at 12Z on the 29th, you can see that there's a very shallow nocturnal inversion that's set up over on the Florida Peninsula. Over 100 or 200 meters, the temperature rises almost 10 degrees C over that time. So again, if you go back to what we're looking at from the sensor, we're looking at 10.3, we're looking at almost all radiation that's emitted right from the surface of the Earth. So essentially, we're looking at the skin temperature of the Earth in the morning before sunrise. So it's going to be as cold, or as we saw, colder than the 2-meter temperature. But when you're looking at 12.3, it's looking at an average of both that skin temperature and also the temperature from it where moisture is water vapor is reabsorbing it, and that can go all the way up to almost 700 millibars in this sounding. And in fact, if you look at the sounding, you can see that temperatures up to about 860 millibars are warmer than the surface temperature. So as this moisture gets absorbed and re-emitted by water vapor, it's actually reabsorbing as warm or warmer air, re-emitting at as warm or warmer temperatures than is the skin temperature of the Earth until you get above 850 millibars. And so the average through that layer is to have the same average temperature, brightness temperature, as you see at 10.3. But as we go later into the day and the sun warms up the atmosphere, and assuming there's not a lot of thermal advection or moisture advection, which Florida was under near high pressure this day, you can see that based on the temperature, you see how the boundary layer warms, mixes up to right around 800 millibars, assuming no change. And now our surface temperature is much warmer than any temperature above the surface. And again, since we're looking at skin temperature at this time, it's even warmer than the 2-meter temperature from Winter Haven, which is sounding space, which my thick red line is based on. And so now that you're much warmer, what's happening is if there has not been a lot of advection at these other levels, essentially the skin temperature is a lot higher at 10, is being measured from 10.3, but the average layer temperature between 700 and 1,000 and the surface is cooler than that skin temperature. And as the boundary layer deepens, then you see that as the boundary layer deepens, you see that temperature difference increase over time because the skin temperature gets warmer and warmer much more quickly than the depth of the boundary layer. And so what we're essentially watching in Florida is we're watching the erosion of the nocturnal inversion. And in fact, as you hit that plateau around 6 degrees difference, you actually can see the boundary layer has hit its convective temperature, and you can see the cumulus begin to form. In this case, there's a strong cap above that, so you aren't going to get convection to form. But it's an interesting way to actually watch how nocturnal inversions weaken over time and get an idea when cumulus may develop, which could have implications for something as simple as aviation, looking at cloud heights for aviation, or when the clouds may form in aviation for aviation interests, or potentially convective development if you can get warmer than the cap altogether. So when we go back and look at our graphs again, you can see that, again, like I said, you're looking at essentially this increasing linear increase is basically the erosion of that nocturnal inversion. And then once you reach the convective temperature, we see that the variation in reflectance and temperature is basically due to a mix of sampling of cloud top temperatures and ground temperatures, since it was not fully overcast over the area. So you'll see a variation over time depending on the percentage of the fractional area of the pixels that's covered with clouds. So what I kind of told my staff about this is that when you're looking at the difference in brightness temperature between 10.3 and 12.3, it's affected by moisture at the level where radiation is emitted. So if you have a strong inversion that exists, then the 12.3 temperature can be as warm or even warmer than the 10.3 brightness temperature. And then as that inversion erodes, you'll see the brightness temperature difference provide information on the changes in that inversion. And if that brightness temperature doesn't change, that may be giving you information that the inversion is going to stay stronger for a longer period of time. And as we saw here, it doesn't say anything about the moisture changes at all, since in this case, the surface moisture actually decreased during the time that the brightness temperature was actually increasing. So it's really important to be aware of the thermal and moisture profiles from soundings, whether model soundings or, better yet, probably observed soundings if you have one nearby, to understand why the brightness temperature difference is changing over time. So what we're going to start doing here is we're going to start using 4 panels. So we aren't just looking at the split window difference or the brightness temperature difference, but we look at the individual different channels as well, the 10.3, the 12.3, and then either a visible channel if it's during the day or some type of IR channel at night that has observations on it. And then watch those evolve over time so that we can see how the different temperatures are changing and if there's cloud cover that's affecting it as well. And be aware that, while I showed you a sunrise example, the same thing would happen in reverse at sunset with clear skies and high pressure. As the temperatures cool at the surface, you will see the brightness temperature difference should decrease until they're near zero when a very strong nocturnal inversion develops. So if you see these rapid changes in brightness temperature, it's really critical to look at your soundings, look at your observations, and make sure you understand why those changes are occurring so you don't misdiagnose what's going to happen. So what I'm going to do next is just go through the loop of the 4 panel that I described above, just showing you how it works, or how it looks during that day. And so up in my upper left is the 10.3, lower left is 12.3, red reflectance is 0.64, which since we're before sunrise is dark, and then the moisture difference or split window difference is in the lower right. And then here's the graph, and you can watch the graph go populate as we move through the time. And what really focus on is Florida, where you can see it's near zero over the entire peninsula, and then the near ocean area, which still has a brightness temperature difference because, of course, the ocean waters in the Gulf of Mexico and the Gulf Stream areas are warmer than the air mass above them in this case. So you see, and there's very little change. So you'll see very little change in brightness temperature difference over these areas compared to the Florida Peninsula. So starting off here, and as we head through sunrise and we head towards 13Z here, notice that right around 1312Z, that there's almost no difference in the brightness temperature difference between the ocean and Florida at this point. So essentially the boundary layer over Florida, at least in terms of brightness temperature difference, is somewhat similar. You have it's starting to warm up that layer. But as we continue to get the solar heating through the day, you'll see Florida start peaking out as being much warmer, much higher brightness temperature differences than the surrounding ocean. See the blue starting to appear at 15Z, and then as you watch on the visible, right around 16Z, you'll start seeing cumulus begin to form over southern Florida, and that's about the time we start seeing the fluctuations in the brightness temperature and the brightness temperature differences over time until we hit 17Z. So it's just a really, I thought, kind of cool example of how you can actually monitor inversion strength changes over time using this channel. Just a week later, actually, Scott caught a really good example of moisture differences across the southern and central plains. So this is from April 7th, 14Z. You see the lighter pinks here over Missouri and Arkansas, the darker pinks here over Oklahoma and Kansas. And that is really showing up as being an area with smaller split window differences over the east, Mississippi Valley, and larger split window differences over the plains. And so you get less moisture here, lots of moisture here, and a really nice gradient in moisture up in the eastern plains, separating Missouri and Kansas, etc. And when you throw up 850 millibar dew points, you can see a gradient in 850 millibar dew points near the same area. But notice that gradient is actually not right over where the difference in shading is, and that's because you're looking at a layer difference in temperature and moisture. You're not looking at one specific level. So looking at a specific level may not tell you exactly where the moisture difference is. There's also the chance that the model could also be off a little bit as well, potentially. But a couple things about this. First of all, this is not the best enhancement. It's the default that you will get if you load the split window difference 10 minus 12 off of AWIPS directly. So you don't want to usually stick with this enhancement. And why is that? Well, it's highlighting these higher clouds to the east. And you get these white where you have 10 to 15 difference in temperature, but those are with cirrus. That really is not what we're looking at this channel for. We're looking at the channel for the differences in the low levels of the atmosphere. So your eye is drawn to areas that aren't really that important. The other thing is that low values can also be important. Not in this specific example, but you can actually see dust. And those will actually have negative split window difference values because of the fact that dust will emit radiation at the temperature where it's at 10.3 very effectively. And so it will actually be colder than the 12.3 temperatures. And there's some available training on this on the MedEd site, which is what I looked at to kind of find out more about this. And if you have questions about that, I know Scott and Dan can probably provide more information on that as well. Here's a different enhancement that makes it a little bit easier to see that difference. The nice grays where it's drier over the Mississippi Valley, and the bright yellows where it's more moist over those southern and central plains. And so your eye is much more drawn to this gradient over Kansas and Arkansas than it was earlier. And also notice, by using the 1,000 or surface of 700 millibar mean dew points, the gradient in the mean dew point layer is right in the same area where our difference in the split window difference is maximized. And even as brightness temperatures may change across the area, usually the gradient is going to remain in the same place because the moisture is, in this case, is driving the change in temperature spatially across the area, not the change in temperature itself or sunrise or sunset. The last thing I want to point out is a really good paper by Dan Lindsay that looked at the GOES-R split window difference using both model data, since this paper was written in 2014 before GOES-R, but also using Meteosat data out of Europe. It's a fairly short paper, about 10 pages. It's a pretty fast read, and it really denotes nicely why you should see these differences and the potential to see pooling of moisture prior to convective development. So again, the split window difference is affected by both moisture and by the emitting temperature of the layer or surface you're looking at. And a couple things to be aware of, other than the inversion example that I showed you, is also be aware of whether you're looking over a cold or warm water surface. Yesterday I was looking at this channel over the Great Lakes, and it's constantly the values were near zero or below zero because the surface, the Great Lakes, were much colder than the air above it. So the skin temperature was nearly, well, not much colder, but the same as the air above it. So the temperature difference was near zero. You can also get that if you compare snow-covered land at the surface to bare land. You'll see near negative numbers with snow-covered land in a time of period where there is warm air aloft, and that you can do that any time now looking over the Colorado Rockies, for instance. And again, the real critical thing with this channel for convective forecasting is looking for those gradients in the split window difference that will show moisture boundaries, because that can be where there's moisture convergence, where you may get lift, and where you may get the first signs that convection development is imminent across the area. So again, here's my email, and I'll be happy to take any questions.
Thanks, Phil. I don't see any questions that have been submitted, so if anyone wants to shout them out, unmute yourself and go for it. Final call for questions. Well, this is Scott, and I will say thank you very much to Phil. Again, if you see something in GO16 and you want to give a similar type telecon, please contact either me, Scott.Lindstrom at NOAA.gov, or Dan.Bikos at NOAA.gov, and we'll help you get set up. And a million thanks to Phil for starting us off here. Thanks.
But thanks, Scott and Dan. Thanks a lot for all your help in this too.